In August 1975, in central China, a great dam, a dam so strong, so well built, that engineers had nicknamed it the Iron Dam, failed in the middle of the night and released a wall of water across the sleeping countryside. The dam was called Banqiao, and it did not fail because it was badly built. The Banqiao Dam was, by the engineering standards used to design it, a sound structure. It failed because of a number. When the dam was designed, engineers had asked a question: how big is the worst flood this dam will ever have to survive? And they had answered it with a calculation. They had computed the size of a flood so rare it should appear. On average, only once in 1,000 years, they built the dam to hold that flood and a margin beyond it. And they called it safe. And then, in August 1975, a storm arrived that was bigger, not a little bigger, far bigger than the 1,000-year flood the dam had been built to survive. The number had been wrong, not the arithmetic. The arithmetic was fine. The number was wrong because of something much deeper and much harder about what it even means to calculate the rarity of a thing. The Banqiao Dam failed, and it did not fail alone. And the loss of life that followed is counted among the worst of any structural disaster in human history. This is the story of the dam built to survive 1,000 years. To understand the failure of the Banqiao Dam, you have to understand what it was for and the era that built it. The Banqiao Dam was constructed in the early 1950s in Henan Province, in central China, on a river called the Ru River. It was part of an enormous, ambitious program of dam building across China in that period, a program with two great purposes. The first was flood control. The rivers of this region had a long, terrible history of catastrophic flooding, and dams were meant to tame them, to hold back the floodwaters and protect the people downstream. The second purpose was to store water for irrigation and to generate power. So a dam like Banqiao was, in the minds of the people who built it, a protective structure, a guardian. It existed, above all, to stop floods from reaching the towns and farmland, and millions of people who lived downstream of it. That is the bitter irony at the center of this story, and it is worth holding from the very start. The Banqiao Dam was built to protect people from floods, and when it failed, it became the source of the worst flood of all. Now, the Banqiao Dam was an earthen dam, also called an embankment dam, and you need to understand what that means because the type of the dam shapes how it can fail. An earthen dam is at its heart exactly what it sounds like: a vast, carefully engineered bank of compacted earth and clay, built across a river valley to hold back water. It is not a wall of concrete, it is a mountain of soil, shaped and packed and layered with great care, wide at the base and narrower at the top, designed so that its own enormous weight and the strength of the compacted material resist the push of the reservoir behind it. Earthen dams are common, and they can be excellent structures. They are often cheaper and simpler to build than concrete dams, especially with a large available workforce. But an earthen dam has one particular defining vulnerability, and it is the vulnerability that matters in this story. An earthen dam must never ever be allowed to be overtopped. Overtopping means water rising so high in the reservoir that it spills over the top of the dam itself. When water flows over the top of a concrete dam, the concrete can often survive it. But when water flows over the top of an earthen dam, the flowing water begins to erode the earth. It carves into the soil of the dam's surface, cutting a channel, and that channel grows and deepens and widens. An earthen dam that is overtopped can be eaten away by the very water flowing over it. And once that erosion begins in earnest, the dam can unravel. The whole structure can be lost. Now, the engineers who built Banqiao understood this perfectly well. An earthen dam must not be overtopped. That is not an obscure fact. It is fundamental dam engineering. So the dam was designed with that danger explicitly in mind. The protection against overtopping has two parts. The first is simply the height of the dam itself and the storage capacity of the reservoir. The dam is built tall enough that an enormous volume of incoming floodwater can be absorbed by the rising reservoir without the water ever reaching the crest. The second part is the spillway. A spillway is a structure, a channel, a set of gates, an outlet, designed to let water out of the reservoir in a controlled way when the level gets too high. The spillway is the safety valve. When a big flood comes in and the reservoir rises, the spillway releases water downstream, deliberately and in a controlled fashion, fast enough that the reservoir level stops rising before it reaches the top of the dam. So the safety of an earthen dam against overtopping comes down to a contest. Floodwater pouring in, raising the reservoir, against the dam's height and storage absorbing it, and the spillway letting it back out. As long as the storage and the spillway together can keep pace with the worst flood that ever actually arrives, the dam is safe. And so the entire safety of the Banqiao Dam rested on one question: What was the worst flood that would ever actually arrive? So how do engineers answer that question? What is the worst flood the dam will ever have to face? This is the genuine intellectual heart of this episode, and it is more subtle and more profound than it first appears. You cannot simply look up the worst flood that will ever happen. The future has not occurred yet. Nobody can hand you the largest flood of the next 1,000 years. So engineers do something else. They turn the question into a question of probability. They use a concept called the return period. The return period of a flood is a way of describing how rare a flood of a given size is. A flood with a return period of 100 years is a flood so large that, on average, you would expect one of that size or larger to occur roughly once every 100 years. A flood with a return period of 1,000 years is even rarer. So large that, on average, one of that size or larger comes along only about once every 1,000 years. So the bigger the return period, the rarer and the more extreme the flood. And a dam is designed against a flood of a chosen return period. The engineers decide this dam will be built to safely handle, say, the 1,000-year flood. They calculate how big that 1,000-year flood is. They make sure the dam's storage and spillway can handle it. And then they declare the dam safe to that standard. Now, I have to be very careful and very honest about what a return period actually means, because it is one of the most widely misunderstood ideas in all of engineering. And the misunderstanding is part of this story. When people hear 1,000-year flood, they very often hear it as a kind of promise. They hear this flood happens once every 1,000 years, so if it happened recently, we are safe for a long time. And if it has not happened in living memory, we are surely due, but not yet. That is not what it means. That reading is wrong, and the wrongness is dangerous. A 1,000-year flood does not arrive on a schedule. The phrase does not mean one occurs every 1,000 years like clockwork. It means something purely statistical. In any single year, the probability of a flood that large or larger is about 1 in 1,000. 1 in 1,000 every year, independently. And here is the unsettling consequence. Because each year is an independent roll of the dice, a 1,000-year flood can happen this year. It can happen next year too. It can happen twice in a decade. The dice have no memory. The fact that a rare flood occurred recently does not lower the odds for next year at all. The return period is a statement about probability, not about timing, and treating it as a statement about timing. Treating 1,000-year as a comforting promise of 1,000 quiet years is exactly the kind of error that lulls people into trusting a dam too much. So the return period is a probability, but that raises an even harder question, and this is the deepest point in the whole episode. Where does the number actually come from? How does an engineer calculate how big the 1,000-year flood is when nobody has watched 1,000 years of floods? The answer is that they extrapolate from the historical record. They take whatever data exists, records of rainfall, records of river flows, historical accounts of past floods, covering however many years that record happens to span, perhaps a few decades, perhaps with older accounts, somewhat longer. And from that limited record of observed floods, they build a statistical model, a mathematical curve that describes how often floods of each size have occurred, and then they extend that curve outward beyond the range of anything actually observed. To estimate the size of floods rarer than anything in the record, they extrapolate the curve out to the 1,000-year point and read off a number. Do you see the fragility in that? The 1,000-year flood is not a measured thing. It is a projection. It is the answer you get by taking a short record of the past, fitting a curve to it, and stretching that curve far beyond where any real data exists. The number is only as good as the record it was built from, and only as good as the assumption that the curve you fitted keeps behaving, far out in the extreme tail, the way it behaved in the modest middle, where your data actually lived. And both of those things, the shortness of the record and the behavior of the tail, were where Banqiao's number went wrong. So the Banqiao Dam was built in the 1,950 seconds, designed against a flood of great rarity, with storage and a spillway size to handle it. And there is one more piece of the dam's history you need because it deepens the tragedy. In its early years, the dam developed cracking problems, and it was subsequently reinforced and strengthened with help from Soviet engineers. After that strengthening, the dam was considered exceptionally robust. It was, in fact, this reputation for strength that earned it its nickname. People called the Banqiao Dam the Iron Dam, a structure that it was felt simply could not fail. So by the 1,970 seconds, here was the situation. A major earthen dam, reinforced and strengthened, widely trusted, designed to survive a flood of around 1,000-year rarity, holding back a large reservoir, with millions of people living in the river plains downstream of it. And in August 1975, the weather did something that the dam's design number had no answer for. In early August 1975, a typhoon, a great tropical storm, moved inland over China. Typhoons usually weaken quickly once they move over land, away from the warm ocean water that feeds them. But this storm, Typhoon Nina, did something unusual and deadly. After moving inland, it stalled. It collided with a cold front and a particular weather pattern that held it in place over Henan province, and it did not move on. A stalled storm does not spread its rain over a wide tract of countryside. It dumps it, all of it, on one place for as long as it stays. And so over the Banqiao Dam's river basin, in the first days of August 1975, there fell an almost unimaginable quantity of rain. The rainfall figures from that event are staggering. In the worst-hit areas, the storm delivered, in a single day, a quantity of rain comparable to what the region would normally expect across an entire year. The downpour over those few days vastly exceeded anything in the local records. This was not the thousand-year storm. The dam had been built to survive. By the measures used to characterize such events, the rainfall was far more extreme than that. An event whose like did not appear anywhere in the historical record the dam's design had been based on. The sky was delivering a flood from beyond the end of the curve. So now follow what that rain did to the contest at the dam. All of that water falling across the river basin ran off the saturated land and into the rivers, and the rivers carried it into the reservoir behind the Banqiao Dam. The inflow, the floodwater pouring into the reservoir, was enormous, far beyond what the dam's designers had ever reckoned with. The reservoir level began to climb fast. And the spillway, the safety valve, the structure meant to release water and stop the reservoir from overtopping the dam, could not keep pace. The spillway had been sized for the design flood. The flood that had actually arrived was far larger. The spillway simply could not release water fast enough to match the monstrous inflow. There were also reports that the ability to release water had been worsened by the difficulty of communication and decision-making during the chaos of the storm. So the contest was lost. Water was coming into the reservoir far faster than the storage, and the spillway together could deal with it. The reservoir level rose and rose and rose, climbing toward the crest of the earthen dam. And on an earthen dam, the crest is the threshold of catastrophe. So now we reach the question at the heart of this story. The dam was built to survive a flood of around 1,000-year rarity. How did a flood so much bigger than that arrive, and what does it really tell us? To understand this, we have to think very carefully about that extrapolated number and about two distinct ways it can betray you. The first way is the shortness of the record. Remember how the 1,000-year flood is estimated. You take the historical record of floods, however long it is. You fit a statistical curve, and you extend that curve out to the 1,000-year point. Now suppose your historical record is only a few decades long. A few decades is a tiny, tiny sample of the behavior of a river basin. In a few decades, you have simply not seen what the climate and the geography of that basin are truly capable of. The most extreme storm in your record might be nowhere near the most extreme storm the basin can actually produce, a rare, monstrous rainfall pattern. Like a typhoon stalling in exactly the wrong place, might be entirely absent from your few decades of data, not because it cannot happen, but because it simply has not happened to happen during the short window you watched. So when you fit a curve to that short record and extend it, you are extending a curve drawn from an unrepresentative sample. The curve does not know about the catastrophe it never witnessed. And the 1,000-year number you read off, it can be far too small. The second way the number can betray you is deeper and more mathematical, and it is genuinely beautiful, in a frightening way. It is about the shape of the tail. When engineers fit a statistical curve to flood data, they are choosing a particular mathematical shape for how rare events behave, and the part of that curve that matters for a dam is the far end, the extreme tail, where the rarest, largest floods live. Here is the problem. Your data lives in the middle of the curve, the ordinary moderately sized floods that occur often enough to be observed. The extreme tail is the region where you have little or no data at all. So the behavior of the curve out in the tail is not really measured, it is assumed. It comes from the choice of mathematical model, and different reasonable-looking models, all fitting your middle-of-the-range data about equally well, can disagree wildly about the tail. One model might say the 1,000-year flood is a certain size. Another model, also consistent with your data, might say floods of that rarity are dramatically larger. The middle of the curve does not pin down the tail, and the tail is the only part a dam actually cares about. So the 1,000-year flood number carries a hidden, often unstated uncertainty. An uncertainty that comes not from measurement error, but from the unprovable assumption that the particular curve you chose keeps behaving correctly, in a region where you have nothing to check it against. The number looks precise, thousand-year flood, a clean, confident figure, but underneath that clean figure is a deep structural uncertainty about the very shape of rareness itself. And now I want to give you the idea that makes this the strangest equation of all, because it is an equation about the limits of equations. Most of the disasters on this channel involve an equation that was missing or wrong or in the wrong field. But the flood probability equation was not missing. It was right there. The engineers computed a thousand-year flood, and the arithmetic of that computation was perfectly correct. The strange thing about Banqiao is that the equation was a confident-looking machine for producing a number that felt like knowledge, that felt like a measurement of the future, when in truth it was something humbler and more dangerous. It was a projection, built on a short record and an unprovable assumption about the tail, and dressed up in the clothing of a precise fact. The deepest error at Banqiao was not a miscalculation, it was a category error. It was mistaking a fragile extrapolation for a solid measurement. It was looking at the words thousand-year flood and believing they described the river, when really they described our limited and uncertain model of the river. An ordinary equation, mass times acceleration, force on a beam, takes solid inputs and gives you a solid answer. But the flood probability equation takes an incomplete past and asks it to testify about an unbounded future. And the past on the witness stand can only tell you what it happened to see. Banqiao was destroyed by the gap between what a number appears to promise and what it can actually know. So let us actually write down the equation, the relationship at the center of the Banqiao disaster. It comes in two parts, and the first part is the simple physical one. The contest at the dam. The rate at which the reservoir level rises depends on the difference between the inflow and the outflow. Water coming in from the flood minus water going out through the spillway. If inflow exceeds outflow, the reservoir rises. The bigger the gap between them, the faster it rises. And if the reservoir rises all the way to the crest of an earthen dam, the dam is overtopped, and overtopping erodes an earthen dam toward failure. That part is just the physics of water in a basin. Inflow minus outflow sets the rate of rise. It is not where the disaster truly lived. The disaster lived in the second part of the equation, the part that decided how big the inflow could ever be, the flood probability equation. Here is the structure of that second equation. The size of the design flood, the worst flood the dam is built to handle, is computed as a function of two things. 1. The historical record of floods. 2. A chosen statistical model that takes that record and extends it out to a chosen return period. Design flood equals the historical record processed through a statistical model, evaluated at the chosen return period. Now look hard at the inputs to that equation because this is where everything turned. The chosen return period, 1,000 years, was a policy decision, a choice of how safe to aim for. That part was a deliberate, visible choice. But the other two inputs were the silent killers. The historical record was short, too short to contain the kind of stalled typhoon catastrophe that the basin could actually produce. And the statistical model carried an assumption about the shape of the extreme tail, an assumption that could not be checked against data, because there was no data that far out. So the equation took a short, unrepresentative record and an unprovable tail assumption, and it produced a confident looking number for the 1,000-year flood. And that number was the size of the inflow the dam was built to survive. The whole safety of the structure rested on it. The arithmetic that turned the record into the number was flawless. The number was wrong anyway, because the record was too short, and the tail was assumed, and no amount of correct arithmetic can repair an input that does not contain the truth. Now I want to make the consequence concrete, because there is a number that captures the whole tragedy. When engineers and analysts later studied the August 1975 storm and flood, the rainfall and the resulting flood were characterized as being far rarer and far larger than the design event the dam had been built for. By some assessments, the flood was on the order of what you might call a several thousand-year, or even rarer, event by the standards of the original analysis. An event from far out in the tail, far beyond the 1,000-year point the dam was designed around. Sit with what that means. It does not mean the engineers did the 1,000-year arithmetic incorrectly. It means the real river, the real climate, the real geography, was capable of producing a flood from a part of the tail that the dam's design number had effectively assumed away. The design said, floods this large are so rare we need not build for them. The sky said otherwise. And once the inflow from that beyond design flood overwhelmed the spillway, the simple physical equation took over. Inflow vastly exceeded outflow. The reservoir rose. It rose to the crest of the Banqiao Dam. and then over it. And the water flowing over the top of that great earthen dam began, in the darkness, to do exactly what flowing water does to an earthen dam. It began to cut it away. So let us go to the dam itself, on the night of the 8th of August, 1975, with the equation in hand. The reservoir behind the Banqiao Dam had been climbing all through the catastrophic rains. The spillway, overwhelmed, could not release water fast enough. The level reached the crest, and in the early hours of the morning, the water went over the top of the iron dam. Once the overtopping began, the outcome followed the physics. The water flowing over the crest eroded into the earthen structure, cutting a channel, and the channel deepened and widened with terrifying speed. The breach grew, and as it grew, the opening through which the reservoir could escape became larger, and the flow became more violent, which eroded the breach faster still. It was a runaway process, a failure that once truly underway accelerated itself. And then the Banqiao Dam failed. The reservoir behind it, an immense stored volume of floodwater, swollen far beyond the dam's design by days of monstrous rain, was released almost all at once into the valley below. A wall of water of almost incomprehensible scale surged downstream into the night, and here is the part of the Banqiao disaster that makes it one of the worst in the history of engineering. The Banqiao Dam did not fail alone. Banqiao was one dam in a large system of dams across that region, and the same monstrous storm that overwhelmed Banqiao was overwhelming other dams at the same time. When the Banqiao Dam failed and released its reservoir, that colossal surge of water flowed downstream, and it reached other smaller dams, and the arrival of that surge, on top of the floodwater those dams were already struggling with, caused them to fail too. The failure of Banqiao helped trigger a cascade. Numerous dams in the region failed in that catastrophe, a chain of collapses, one releasing its water onto the next. The result was a flood across the plains of Henan province of staggering extent. Vast areas inundated towns and villages and farmland across a huge region swept by water. The human catastrophe that followed was immense. The loss of life from the Banqiao failure, and the wider chain of dam failures, and flooding it, was part of, is counted among the deadliest structural disasters ever recorded. The estimates of the death toll vary very widely between sources, and the full figure, including those who died in the immediate floodwater, and those who died afterward in the disease and famine that followed in the cut-off, devastated region, has been the subject of much later study and disagreement. But by every account, the number of dead was very large, and the suffering across that region was on a scale that is difficult to take in. In the aftermath, enormous efforts were made to rescue survivors and to relieve the cut-off region, including military operations to reach areas that the floodwater had isolated. And in the years and decades that followed, the Banqiao disaster became a subject of intense engineering study. The dam was eventually rebuilt. A new Banqiao Dam was constructed at the site, designed to far more demanding standards, with a vastly greater capacity to pass floodwater. But the deeper legacy of the 1975 failure was what it taught the worldwide community of dam engineers about the design flood itself, about the danger hidden inside that confident-looking number. Banqiao became one of the most important case studies in the world for the field of dam safety and flood hydrology. A permanent, terrible demonstration of what happens when a dam is built against a design flood that the real climate can exceed. The Iron Dam had failed, and the lesson it left behind was written in one of the highest costs any engineering lesson has ever carried. So how does an engineering profession respond to a disaster like Banqiao? How do you design against a flood when you now know with terrible certainty that your estimate of the worst flood can be wrong? The response was not to abandon the idea of the design flood. You cannot design a dam against no number at all. The response was to treat that number with far more humility and to build in far more protection against the possibility that it is too small. Several deep changes came out of Banqiao and the broader history of dam failures around the world. The first is the rise of a concept that goes beyond the thousand-year flood. For the most critical dams, dams whose failure would kill large numbers of people, modern engineering increasingly designs not against a flood of a chosen return period, but against something called the probable maximum flood. The probable maximum flood is an estimate built from meteorology and hydrology of the most extreme flood that is physically possible for that particular river basin. The flood you would get from the most extreme rainfall the atmosphere could conceivably deliver to that place. It is, in essence, an attempt to find not the thousand-year number, but the ceiling, the worst that nature could ever physically do. And critical dams are designed so that even the probable maximum flood can be safely passed without overtopping. It is a deliberate move away from probability, away from return periods, toward a physical upper bound, precisely because Banqiao showed how dangerous it is to design against a flood that the real world can exceed. The second great change was about the cascade, about the fact that Banqiao did not fail alone. The 1975 disaster showed in the most brutal way that dams in a river system are not independent. The failure of one can trigger the failure of others downstream. So modern dam safety treats systems of dams as systems, analyzing how the failure of an upstream dam would load the dams below it, and designing and managing the whole network with that cascade risk in mind. The third change was about the spillway and about communication and operation. Banqiao's ability to release water was overwhelmed and worsened by the chaos and the breakdown of communication during the storm. Modern practice puts great emphasis on spillways with enormous capacity, on emergency action plans, on reliable communication and monitoring, and on the ability to make and execute release decisions even in the middle of a catastrophe. And the fourth change is perhaps the most important and the hardest. It is a change in attitude. Banqiao taught the profession to treat the design flood not as a fact, but as an estimate carrying deep uncertainty, and to ask always the question that the builders of the Iron Dam did not ask hard enough. Not just how big is the worst flood we expect, but what happens if we are wrong? What happens if a flood larger than our number actually comes? A well-designed modern dam has an answer to that question. It is designed so that being wrong about the number is survivable. And there is a deep idea in all of this, an idea worth stating plainly. The lesson of Banqiao is not that engineers should compute the design flood more accurately. It is true that longer records and better models help, and in the decades since 1975, flood hydrology has improved enormously, but the deeper lesson is humbler than better arithmetic. The lesson is that some numbers by their very nature cannot be known with the confidence they appear to offer. The size of the thousand-year flood is a projection from limited data into an uncertain tale, and no amount of cleverness fully removes that uncertainty. So the truly safe response is not to trust the number more. It is to design so that you do not have to build in margin, to design against a physical ceiling rather than a probability, to assume structurally that your best estimate of the worst flood might be exceeded, and to make sure that when it is, the dam and the people downstream survive anyway. Banqiao was built to trust a number. Modern dam safety, taught by Banqiao, is built to survive the number being wrong. The failure of the Banqiao Dam is now, in engineering education worldwide, one of the most important case studies in the field. It is taught in dam engineering and hydrology as the defining lesson in the design flood, in the danger of building a dam against an estimate of flood probability that the real climate can exceed. It is taught in risk analysis as a model of cascade failure, of how the collapse of one element in a connected system can bring down the others. And it is taught more broadly in the study of probability and statistics as one of the great cautionary tales about extrapolation, about the peril of taking a short record of the past, fitting a curve, and trusting that curve far out in a tale where no data lives. All of those readings are true. But here is the thing about Banqiao that I find most haunting, and it is the thing that connects it to every story on this channel, and also makes it, in one specific way, unlike any of them. On this channel, the usual pattern is a missing equation, metacentric height, aeroelastic flutter, synchronous lateral excitation. In each case, the mathematics that would have explained the disaster did not yet exist, or was hidden, or was ignored. But Banqiao is not a story of a missing equation. The flood probability equation existed. The engineers used it. They computed a design flood, and the computation was correct. Banqiao is something stranger. It is the story of an equation that worked exactly as designed, and was still not enough, because the equation was never the kind of thing it appeared to be. It appeared to deliver a fact, the size of the thousand-year flood, a clean and confident number, but it actually delivered a fragile projection, built on a record too short to contain the basin's true capacity for catastrophe, and on an assumption about the tail that could not be checked. Every other disaster on this channel teaches us to find the missing equation, to write it down, to bring it into the room. Banqiao teaches the opposite and harder lesson. It teaches us that even when the equation is present and correct and faithfully computed, we must still ask what that equation can actually know, and we must build for the possibility that the honest answer is less than we wish. I want to leave you with the thought I find most profound about Banqiao, and it is the reason this story belongs on this channel. We use mathematics to reach into the future. That is, in a sense, the whole purpose of an equation in engineering to tell us before we build what the world will do to the thing we are building. And mostly this works. The equation for the strength of a beam tells us reliably whether the beam will hold. The equation for an orbit tells us reliably where the spacecraft will go. But Banqiao is about a different kind of equation, an equation that reaches not into the predictable future, but into the future of rare and extreme events. And that kind of equation is fundamentally humbler than it looks. Because to know how rare the rarest floods are, you would need to have watched the river for a very, very long time. Far longer than any record we possess. And we have not. We have a short glimpse, and a curve fitted to that glimpse, and a confident-sounding number read off the end of the curve. The thousand-year flood is not a measurement of the river. It is a measurement of our limited knowledge of the river, wearing the costume of a fact. And the deepest lesson of Banqiao is to know the difference. To know when a number is a solid measurement, and when it is a fragile projection from an incomplete past. The river does not care what curve we fitted. The atmosphere does not consult our return periods before it decides where a typhoon will stall. The world is free to produce a flood from a part of the tale we never imagined. And it will, eventually somewhere, do exactly that. Wisdom in engineering is not only knowing the equation, it is knowing what the equation cannot know, and building with humility and with margin for the gap. The Banqiao Dam was rebuilt and stands again on the Ru River, designed now to standards its predecessor never approached. The disaster reshaped dam safety and flood engineering in China and around the world, the rise of the probable maximum flood, the analysis of cascade risk, the deep institutional humility about the design flood number. The Iron Dam failed because it was built to trust a number that the sky was free to exceed, and the cost of that lesson was among the highest any engineering lesson has ever carried. Strange equations are not always strangers, and they are not always missing. Sometimes the equation is right there, correctly computed, and the strangeness is that it quietly promised more certainty than it could ever truly hold. The flood was always possible. It lived, the whole time, in a part of the tale the dam's number had assumed away. The river ran its mathematics on schedule. We had simply, with flawless arithmetic, calculated the wrong worst case. If you enjoyed this one, the story of a spacecraft that traveled hundreds of millions of kilometers to Mars and was then lost in its final minutes. Destroyed because two teams of engineers working on the same mission were quietly using two different systems of units, is a story for another day. Strange Equations is here for the math, behind the moments that nobody at the time was calculating. If that is your kind of channel, subscribe. Thank you for watching.